Feature engineering is the art and science of transforming raw data into meaningful features that enhance machine learning model performance. It is the crucial bridge between raw data and effective machine learning models. Here are some scaling and normalization techniques. First, standard scaler, also known as z-score, transforms features to have a mean of 0 and a variance of 1. It's ideal for algorithms sensitive to feature magnitudes. Next, min-max scaler scales features to a fixed range of 0 to 1. It is best when you need bounded values or dealing with sparse data. Finally, robust scaler uses statistics that are robust to outliers, perfect for data with outliers or extreme values. Here is an example code. From sklearn.preprocessing, import standard scaler. Initialize the scaler with scaler equals standard scaler. Fit and transform the data with x_scaled equals scalar fit_transform of x. For new data, only transform using x_scaled equals scalar transform of x_new. Let's discuss how to handle missing values. First, there's mean or median imputation. This replaces missing values with the mean or median of the column and is suitable for numerical data with random missing patterns. Next is forward or backward fill, which fills missing values using the previous or next valid observation. This method is ideal for time series data. Finally, there is model-based imputation. This uses machine learning models to predict missing values based on other features and is best for complex relationships. Here is some sample code. From pandas import as PD. From sklearn.impute, import simple imputer. Create imputer for mean strategy with imputer equals simple imputer, strategy equals mean. Fit and transform the data using x_imputed equals imputer fit_transform of x. For time series data, use df.fillna, method equals ffill. Here are some ways to encode categorical variables. Label encoding is for ordinal data where red maps to 0, blue maps to 1. One-hot encoding is for nominal data where red maps to the vector 1, 0, 0. Blue maps to the vector 0, 1, 0 and green maps to the vector 0, 0, 1. Target encoding is for high cardinality data where red maps to 0.35 and blue maps to 0.72. Here is some sample code. From sklearn.preprocessing import label encoder. From sklearn.preprocessing import one-hot encoder. Import category encoders as CE. For label encoding, LE equals label encoder. X of category equals transform of X of category. For one-hot encoding, one-hot equals one-hot encoder, sparse equals false. X_encoded equals one-hot transform of X of category. For target encoding, target_length equals a target encoder. X_encoded equals target_length transform X of category Y. Let's explore feature creation and extraction. Polynomial features create interactions between existing features to capture nonlinear relationships. For example, x1 and x2 are transformed into x1 squared, x1 times x2, and x2 squared. Statistical features generate statistical aggregations from existing features such as mean, standard deviation, minimum, maximum, and percentiles. Domain-specific features create features based on domain knowledge and business rules. For example, purchase frequency equals orders divided by time period. Here is some sample code. From sklearn.preprocessing import polynomial features. Import numpy as np. Create polynomial features with poly equals polynomial features degree equals 2. Differentially equals poly.fit_transform of x. Create statistical features with df of rolling underframe equals df of value dot rolling window equals 7 dot mean. Create domain features with df of price equals df of price divided by df of earnings. Create interaction features with df of area equals df of length multiplied by df of width. Here are some feature selection methods. Statistical methods use correlation coefficients, chi-squared tests, or mutual information to identify relevant features, and are best for understanding direct relationships with the target variable. Model-based selection utilizes feature importance scores from tree-based models or lasso regularization to select the most impactful features. Wrapper methods use sequential feature selection, either forward or backward, to iteratively build an optimal feature subset based on model performance. Here's a feature importance visualization showing feature A with an importance score of 0.85, feature B with 0.68, feature C with 0.53, feature D with 0.38, and feature E with 0.25. Here are some dimensionality reduction techniques. Principal component analysis, or PCA, is a linear transformation that maximizes variance along principal components and is best for linear relationships and continuous data. TSNE is a nonlinear dimensionality reduction that preserves local structure and is excellent for visualization and complex patterns. UMAP is a manifold learning technique that balances local and global structure and is fast and effective for large data sets. Here is some sample code. From sklearn.decomposition, import PCA. From sklearn.manifold, import TSNE. Import UMAP. For PCA reduction, PCA equals PCA, underscore components equals 2. X equals PCA underscore transform of X. For TSNE reduction, SNE equals TSNE, underscore components equals 2. Perplexity equals 30. This underscore NE equals SNE. Transform of X. For UMAP reduction, reducer equals UMAP.UMAP. UMAP equals reducer to transform of X. Let's explore time series features. Time-based features extract temporal components from datetime objects such as hour, day, month, year, and day of week. Lagged features create features from previous time steps such as T-1, T-2, T-3, and moving averages. Seasonal features capture recurring patterns in cycles such as is weekend, is holiday, and season. Here is some sample code. Import pandas as PD. For time-based features, df of hour equals df of datetime, hour. df of equals df of datetime, day of week. df of equals df of for S and 5, 6. For lagged features, df of lag equals df of value, shift 1. df of rolling equals df of value, rolling window equals 7 mean. For seasonal decomposition from statsmodels.tsa.seasonal import seasonal to compose. Decomposition equals seasonal compose df of value, period equals 12. Let's explore text feature engineering. Text preprocessing cleans and standardizes text data before feature extraction. Steps in text preprocessing are tokenization, lemmatization, and stop word removal. Text vectorization converts text into numerical features using techniques like bag of words, TF-IDF, and word embeddings. Advanced features extract high-level text characteristics such as sentiment scores, text length, and entity counts. Here is some sample code. From sklearn.feature_extraction, text import TVID vectorizer. From nltk.tokenize import word_tokenize. Import spaCy. For text preprocessing, NLP equals spaCy.load, and doc equals NLP of text. Tokens equal the list comprehension token.lemma for token in doc if not token.is_stop. For TF-IDF vectorization, vectorizer equals TVID vectorizer, max_features equals 1000, ngram_range equals 1, 2. X_viv equals vectorizer of transform of texts. Extract text features. df of text length equals df of text str.length. df of word equals df of text split str.length. Here are some best practices and guidelines for feature engineering. First, exploratory analysis should be performed first. Understand data distribution and relationships before feature engineering, as this helps identify potential transformations and important patterns. Test feature impact. Validate each engineered feature's importance using cross-validation, and remove features that don't improve model performance. Pipeline integration. Implement feature engineering steps in a reproducible pipeline to ensure consistency between training and inference. First, we perform data exploration, then we perform feature engineering, next is validation and testing, and finally pipeline integration. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.